In this video, let us see how a vector quantity can be represented as a phasor. The topic is phasor representation of sinusoidal quantities. Myself is Dr. Nisha, working as faculty in Electrical and Electronics Engineering Department of Jyoti Engineering College. So let us see how a sinusoidal quantity can be represented using phasor. For that, first of all, what is a phasor? Phasor is any vector which is rotating at constant angular velocity. A sinusoidal quantity, it can be a voltage or current, can be represented by using a phasor rotating in anti-clockwise direction with a constant angular velocity omega radians per second. The instantaneous value of the alternating quantity. Here we are considering an alternating sine wave and its reference point is taken as a zero crossing point, and this reference is represented by the x-axis in this phasor diagram, and the alternating quantity is represented by a phasor having length as shown in the figure. This length is equal to the maximum value of this sine wave. At any instant when the sine wave is moving like this, it has different values at different instants. Suppose, consider this point. At this instant, the sine wave has a magnitude which is obtained by projecting this point onto the y-axis. Now, the sine wave is represented by this phasor. The zero crossing point is represented by alignment of phasor along the x-axis. And as the sine wave progresses like this, the phasor rotates anti-clockwise like this. So, this instant is represented by this point on the phasor diagram. The instantaneous value or magnitude at this instant is obtained by projecting the phasor onto the vertical axis. So, this is the magnitude at the instant represented by this point, which is same as the magnitude obtained on the y-axis. So at any instant, the instantaneous value can be obtained by projecting the vector onto the vertical axis. At this point, the vector is aligned along the x-axis and projecting onto the vertical axis, the instantaneous value is obtained as 0. And at this point, the phasor aligns along this direction. See? Phasor rotates and aligns along this direction, and projecting this phasor onto the vertical axis will give you a maximum magnitude represented by the length of the phasor. Now, as the sine wave progresses from 90 degree onto pi onto 180 degree, the phasor rotates counterclockwise along this, and when it reaches pi, the phasor is aligning along the negative x-axis. Further rotation of the sine wave, further progress of the sine wave is represented by rotation of the phasor like this along this circle. And one complete rotation of the phasor represents one complete cycle of the sinusoidal waveform. Now, a diagram which represents the sinusoidal quantity as a phasor is called the phasor diagram. So a phasor diagram can have different phases, one or more phases, but they should have the same frequency. Now we are considering two sine waveform, voltage and current. Current is lagging the voltage by an angle phi. These two quantities, they have the same frequency. They maintain the lag throughout. This zero crossing point lags the zero crossing point of the current lags the zero crossing point of the voltage by phi, and the pi of the current again lags the pi angle of the voltage by angle phi, and that phase lag is maintained throughout. This voltage is represented by the phasor diagram V, and the current is represented by phasor diagram I. The voltage is aligned along the x-axis and the current lags the voltage by phi. So the current vector is drawn at an angle phi in the clockwise direction. Both the phasor is assumed to be rotating anti-clockwise with an angular velocity omega, and the voltage leads the current or current lags the voltage by an angle phi. The phase difference phi between the two waveforms will be the same at all times, and the expression for the instantaneous value is obtained as V is equal to Vm sin omega t and I is equal to Im sin omega t minus phi. Phi here we are representing as minus phi because the current is lagging the voltage, and for obtaining the current phasor we are moving clockwise by an angle phi, so it is taken as minus phi because anti-clockwise direction is taken conventionally as the positive direction. Now these phasors can be represented in rectangular, polar, exponential and trigonometric form. Let us see rectangular form, or it is also called the complex form. In this form, the phasor is represented in terms of a horizontal component and a vertical component, and we make use of an operator called j, where j is equal to square root of minus 1. Now let us see a phasor V1. It has a magnitude represented by the length of the phasor, and it is represented by capital V1, and it makes an angle phi with the reference axis. Now this phasor V1 can be represented as A plus JB, where A is the horizontal component of the phasor and B is the vertical component. A is obtained by projecting the phasor onto the horizontal axis and B is obtained by projecting the phasor onto the vertical axis. Next form of representation is polar form. In polar form, the phasor is represented by a magnitude and a phase angle, which it makes with the reference axis. Now consider a phasor V1 represented by magnitude capital V1 and makes an angle phi with the reference axis. It is represented in polar form as V1 is equal to V1 magnitude angle phi. Now the magnitude V1 is obtained as square root of A square plus B square, where A is the horizontal component and B is the vertical component. So A and B are components in the rectangular form of representation. By using that, we are getting the magnitude for the polar form. Now the angle which the phasor makes with the reference axis is obtained as phi is equal to tan inverse B by A. Now consider another vector V2. It makes an angle minus phi with the reference axis. It is represented in polar form as V2 angle minus phi, where capital V2 is the magnitude of the phasor and V2 is represented as square root of A square plus B square and angle phi is tan inverse minus B by A. Next form of representation is trigonometric form. Now the figure shows a vector V. It has a horizontal component V cos phi and a vertical component V sin phi. It is obtained by projecting the vector onto the x-axis and onto the y-axis. The trigonometric form is represented as V into cos phi plus j sin phi. The exponential form of representation is based on Euler's relation, which is e raised to plus or minus j phi is equal to cos phi plus or minus j sin phi. When the exponent has positive sign, here we are using positive sign. When the exponent has negative sign, here we are using negative sign. For that also, let us consider a phasor V1 having magnitude V1 and making an angle phi with the reference axis, and a phasor V2 having magnitude V2 and making an angle minus phi with the reference axis. Then In exponential form, V1 is represented as capital V1, which is the magnitude, into e raised to j5, and V2 is capital V2 e raised to minus j5. Okay, for now, let us say goodbye. We'll come again with another video. Thank you.